Hello, today we're gonna be doing a tutorial, um, which has been provided by this paper, written by Mohan and other authors in individual tree detection. So they're using UAV derived point clouds and high density LiDAR point clouds to detect trees. So the first things we're gonna do is go to supplementary materials, which is a PDF. Um, they provide with the data and they provide with the code. So we're gonna be going through these steps. So first of all, we need the data. Then we classify the ground points, then build the DTM and normalize the points using the DTM, and then generate the canopy height model. Then there is a function for smoothing, then the detection, and then we supposedly validate using manual inspection, visual inspection, but maybe not today. Um, the first thing, the Gator data, you go to 2019. 2019, here's the Forcio. I've already downloaded it. And to download that, you're gonna get something like this. Um, Once you go inside, there's gonna be these folders. You're gonna bring everything out of there and then just throw it in the main directory. And I have already prepared this over here. So there's a couple of comments about this. So the LiDAR, it is not available. So not available on CRAN. So to download it, you're gonna need to find it. Um, so you need to find it in this contribution archive, and you're gonna find three versions. They specify that they use the first one, but I downloaded this one. You go over here, then you install, and then you browse your tar.gsc and you install it. However, you're gonna need two more packages for it to don't run into any three packages to don't run into any conflict. And I think it's geometry. Um, so and the other one is spats.geom. Put it over here, and then btops for it to be able to install. After you have installed it, so this is not gonna work. Line one doesn't work. You can import it, and then the LiDAR package does works, and you can just import it. Um, so the first thing you need to set your working directory to the main folder, and you can just call it, and then notice that the first point cloud is instruction from motion point cloud, and you use read last for that one. Um, Number equal to 0 found. So let's clean this up. Let's see if we can read it. Yeah, so it's just a warning message. And then notice that the second one, the UAV LiDAR high density, is a bit heavier. So I assume that's why they do read last catalog. So we load those two. We have two point clouds. Then we read the CHPs that are in the folders. Those are the areas of interest. Um, Says mission proj file, but seems to be reading okay. Then they use a library raster, so we have to raster. You raster for this. So you buffer those shapefiles to 3 meters. And now the buffers shapefile, you're gonna use it to clip the area of interest. So you have the point cloud, and then you add your new geometries. You can do that, and then you can plot both, and we can take a look at both. So that looks pretty sparse. So I assume that's UAV, and this looks more dense, so it's probably the Velodyne uh, laser scanner. Um, Next up, we need to classify, like we said. So going back to this, we're in the step two, classify ground points. To classify the ground points, they use a sequence of window sizes. So from 3 to 12, incrementing by 3. So that's probably going to be 3, 6, 9, and 12. 6, 9, and 12. And then they also have a sequence from 0 0.1 to 1.5, incrementing, well, they gotta be the same amount, so just four numbers between those two. And the sequence will do it. So yeah, four numbers between those two numbers, and those are the intermediate points. Then they use this classify ground, which is part of LiDAR. And yeah, they input the point cloud that has been um, cropped, and then they use this function PMF, which uses the window size and the thresholds of size um, to find those ground points. So going through it, it's gonna create two point clouds that have the classified ground points. So we're gonna give it a second, and now we're gonna create a DTM. So again, we're in this part, so we're gonna grab those ground points and we're gonna create a DTM. To do that, we first have to define the grid size, which is 1 meter in this tutorial. Then we use the function grid terrain using that point cloud, and we're specifying we need a DTM, a digital terrain model, and we are using that looks like K nearest neighbors inverse distance weighting um, with the defaults. So we do that, and then we can plot our results, and we get these two terrain models, as you can see there. Next up, we need to normalize. So basically, we're gonna subtract the elevation from the digital terrain model from the points, and this will um, create a point cloud which has a minimum of 0. And we can do that. I'm going over here by normalizing. So we take the grid values and then we subtract it from the every point in the point cloud, and then we get a normalized one. And now we have normalized. Now we're gonna do the CHM function, which is creating a digital model from it. So again, we define our grid cell, and from a grid cell, 50 centimeters, we're gonna create it using the normalized point cloud. We specify we need a CHM. It's like a parameter. This method, which is point to raster, and then we fill the NA. So I'm guessing we're interpolating with key nearest neighbor inverse distance weighting with K equal to 3 and P equal to 2. I guess these are modifiable. That's to find the sites in where we don't have points or yeah, we are interpolating. And then now we have our CHMs, which are rasters. So we have gone from points to rasters. So you are not working anymore with point clouds. Then the next part is a smoothing window. And for the smoothing window, using a filter of 5. Um, Once that parameter is, we're going to call our LiDAR, which a problem's installing it, but should be solved now with a filter mean and our window size. So that should smooth both of those. And so treetop detection local maximum filter window size, or window size is going to be 7 by 7, I believe. And then our minimum height threshold, so any tree below 3 meters is going to be filtered out. And then we're going to use the LiDAR find tree CHM. And you're going to input the CHM and both of our parameters, which are the exclusion parameter, and I believe this is the window size parameter. And that should give us our treetops. And so here, spatial points data frame. So we're creating a data frame, the spatial points of all those points. So this just creates a position or like the treetops list in a data frame that I'm guessing that we're gonna use. So spatial points data frame to not find function. Maybe we can find it in help. So SP, so we need the library SP. So yeah, maybe, yeah, that work. After you get that, now you can plot the CHM and plot the tops, one on top of the other. And then we're gonna be able to see that. So that's one, that's two from each of the sides, right? Right. Um, this is one plot 30 by 30. And those are the trees that we have detected. Now for the exporting part, we're writing rasters, and it seems that we're writing the DTMs, and we're writing the CHMs, and we are getting the treetops out of in a shape file. So I just wanna inspect real quick site 2 T-tops. Looks like so double XY, so positions. You got the heights, you got the coordinates, and yeah, looks like that's what you get. Let's see. We Well, that's good enough. Now we export. Make sure you create these products in your main directory so you can export them to them. If not, you're gonna get an error. Could not find function right raster. Interesting. So if we can write rasters, it's because we need to specify that we're using. So it's in raster, so we should either import the library or add something like this, raster dot dot. But either way works. Right, so if we go here in our products folder, we can see we have our results here. I believe we can open this in the viewer. Yes, it is possible to watch it in the viewer. All right, there. It's a CHM T file, which contains the elevation. And that'll be all. Thanks.